Hello and welcome to a video on graphing exponential and logarithmic functions. So first let's talk about some exponential functions. I've sort of written an example of what an exponential function might look like in general. But we need to talk about like what a, b, and d are, what effects do they have on the function. So a, I usually call the initial value because that's the value that this part of the function, that's the value of this exponential part of the function when x is 0, before you apply any vertical shifts to the function. B is the base value. That normally helps us to determine if the function happens to be exponential growth or decay. D applies a vertical shift to the parent function. And when we talk about the parent function would just be y equals b to the x, just a basic exponential function. So d is either going to shift that function, the parent function, up or down. And y equals d is going to be the equation of the EBA of the end behavior asymptote. And then this is just a very, very important fact to remember, that exponential functions have horizontal asymptotes. I cannot stress that enough. That's extremely important to remember because we'll see that logarithmic functions have vertical asymptotes, and exponential and logarithmic functions, they're inverses of each other, and they're close confusers in the sense that they have a lot of properties that are similar and then some that are different, and students typically tend to get them mixed up a lot. So whatever sort of way you have of remembering that, I implore you to use that way to remember that exponential functions have horizontal asymptotes. So let's look at an example here. F of x equals 2 times 3 to the x minus 4. So I'll talk about these calculator screens in a second, but I just want to write down some of the basic properties of the function. So y equals negative 4 is going to be our EBA, our end behavior asymptote. So I'm just going to go ahead and dash in end behavior asymptote right there. The base value here is 3. That's greater than 1, so this is going to be an exponential growth function. And so I know that in general the function is going to be increasing, but I want to get some points that are on the function. So I'm going to go ahead and make a table, and I want to pick convenient small values for x, because sometimes if you pick large values for x, the function becomes difficult to evaluate. I want to pick small values that I could do without a calculator. So what if x was 0? Well, if x was 0, 3 to the 0 is 1, times 2 is 2, minus 4 is negative 2. So that's 1 point on the function. And I'll pick one more x value. I'll pick 1. 3 to the first power is 3, times 2 is 6, minus 4 is 2. So when you are evaluating these functions for particular values of x, just remember order of operations. Exponents come first, then multiplication and division, and then addition and subtraction. So you have to follow the order of operations. I know this is going to be an increasing exponential growth function, so the graph's going to look something like so. There's my exponential growth function. Then I took my calculator, entered 2 times 3 to the x minus 4. I entered this exponential growth function into y1, and there's the graph. So notice the calculator does not dash in the end behavior asymptote, which you should be doing. You should always, any asymptotes that the function has, dash them in. And then, see, it looks like this function might have a vertical asymptote, but it does not. It's increasing very, very, very rapidly. So there's no vertical asymptote here, because I could have x be 2, I could have x be 3. With exponential functions, x can be anything. So the domain here is negative infinity to infinity for x. I can pick any value I want for x. The function is defined for all values of x. So it looks like there's a vertical asymptote there, but there's no vertical asymptote. There's just a horizontal end behavior asymptote. Now also, the function will never output a y value of -4. The functions, we've got this EBA at y equals -4. The function gets really close to having a y value of -4, but it never actually outputs a y value of -4. But it will output values really, really, really close to -4, like as close as we want, because as x goes to -infinity here, the y values just keep getting closer to -4. But look at the table in the calculator here. So it's not like the calculator is lying, it's just that these values are so close to -4 that the calculator is rounding the output value to be -4. So, I mean, that's technically false. Like when x is -10, y is probably like -3.9999, with just so many nines that the calculator is just rounding to -4. So you got to be careful when you look at the calculator, because with a lot of these functions, it's not that the calculator will lie to you, it's just that the precision of the calculator is very, very limited. The calculator, I mean, like the screens are super pixelated, they're not it's not a high resolution, 4K screen or anything like that. It doesn't have a lot of RAM in the calculator. It's a very simplistic computer that's not very powerful. So sometimes could be deceiving if you're not really, really thinking about like what the outputs mean and what outputs are possible. Like in this case, we know that the function's never going to output -4, so we know that these values in the table can't be correct. That's just rounding error by the calculator. So one thing that you probably want to be pretty careful about is negative exponents, because you look at, here's an example, g of x equals 4 to the -x. It looks like, ooh, this function might be exponential growth. But remember, the way you sort of want to think about negative exponents, so 4 to the -1 times x, or 4 to the -x. So I would rather think about that as 1/4 to the x power. Because remember, if you're evaluating a negative exponent, like what does 4 to the -1, what does that mean? Negative exponents mean you look at the reciprocal of the base and you raise that reciprocal to whatever that power is. So 4 to the -1 really is the same as 1/4 to the 1. So you got to be careful when you've got these negative exponents that you don't get deceived. Like you usually want to take anything with a negative exponent and write it in terms of the exponent not being negative, so it's less confusing. So here, because when you look at 4 to the -x, you might think that that's exponential growth, but it's not. It's exponential decay. That base value is less than 1. So those rules that I had for whether the base is greater than 1 or less than 1 corresponding to exponential growth and decay, those are hinging on you not having a negative x in the exponent there. So you just got to be careful. Be wary of the negative exponents. So now let's talk about logarithmic functions, which they're very closely related to exponential functions because they're inverses. So they have a lot of similarities, but then some important differences. This is the big one that people get mixed up with. Log functions have vertical asymptotes. Exponential functions have horizontal asymptotes. Just you need to not get that confused, and it's hard to not get that confused because they're close. Can get them confused. So whatever you can do to remember that, just do that. It's great. That would be great. So when you look at this function, this horizontal shift is going to dictate where the vertical asymptote is. So x equals c is the vertical asymptote, b is the base of my logarithm here, and then d again is that's the vertical shift. So again, just some basic properties and what a basic log equation might look like, but this is much easier when we look at a concrete example. So here's log base 3 of the quantity x plus 4. So first things first, let's figure out what that vertical asymptote would be. So it would be x equals -4. Let's dash in that vertical asymptote, and the function will never cross that vertical asymptote at x equals -4. Great. Now, I know this equation is going to look like a log graph, but let's get some points on that log graph. And this is where we want to be careful, because with logarithms, with logarithmic functions, you don't just want to blindly choose x values, because you really want to look at what the base is. So I really want this quantity x plus 4 to work out to be a power of 3. So for example, I know that 3 squared is 9. So making this quantity 9 would be great. So if I made x 5, and then I wanted to evaluate this, I'm going to do some scratch work over here. So f of 5 would be log base 3 of 9, because if x is 5, 5 plus 4 is 9. Great. Now remember, when you're evaluating logs, the way that you evaluate log base 3 of 9 is you're thinking to yourself, 3 to what power gives you 9? So when you're evaluating a logarithm, you're usually thinking of an exponent. You're trying to find an exponent given these two values here. 3 is the base. I think of 3 as being the base and 9 as being my answer, so to speak. So I'm taking this base. 3 to what power gives me 9, and that's 2. So this whole thing equals 2. So you can see you don't just want to pick x values at random. You want to make this inside. You want to be thinking about making this whole quantity a power of 3. So we could make x be, say, -1, because -1 plus 4 would be 3. And 3 to what power is 3? The first power. We could make x -3, because -3 plus 4 is 1, and 3 to the 0 power is 1. I want to write that one out. So f of -3 would be log base 3 of 1, because if x is -3, -3 plus 4 is 1. Now here it's 3 is my base value. Thinking of 1 as being the answer, like 3 to what power gives me 1? 0. Because any positive number to the 0 power is 1. So let's plot all these points. We've got -3, 0. We've got -1, 1. And we've got 5, 2. So now I can draw on the graph, and I'm just going to hug that vertical asymptote, and then go through those points, and then continue to grow very slowly. So again, logarithmic functions have vertical asymptotes. It may appear that this function has a horizontal asymptote, but it does not. It keeps increasing out to infinity, just very, very, very slowly. So there's an example of a logarithmic function. Now, I picked the base to be 3 here on purpose because the calculator is not really great for dealing with logarithmic functions. I mean, there's some sophisticated tricks we could employ, but just in general, so here's our function, log base 3 of x plus 4. So a lot of people would open up y equals and graph log of x plus 4. But on the calculator, like if you on the calculator, when you do log of x plus 4, typically in most math books, and most certainly for the calculator, when you just write down log with no base, the base is an implied 10. So here on the calculator, when you type in log of x plus 4, that's really log base 10 of x plus 4. Like, that's not even the function that I want. So like, if I wanted to graph this f of x, this right here, this log of x plus 4, that's not it. So you got to be really careful, because the calculator doesn't have a log base 3 button. Well, some of the newer calculators do, but most of them do not. Then furthermore, I mean, look at what this calculator did. Okay, so it's the graph. This over here is the graph of log base 10 of x plus 4. So look at this. This graph should, even though these functions are different, they do have the vertical asymptote is in the same position for both of these functions. So I should, even though the function is going to have slightly different points compared to f of x over here, there still should be a vertical asymptote at x equals -4. But look at this. The calculator just sort of like stops the graph there. Again, there's just rounding error in the calculator, and this screen is not very high resolution. So there should be a vertical asymptote here at -4, which the calculator doesn't draw in, and then the graph should continue down like that, and then up very, very, very slowly, like so. That's what the graph should be looking like. But like I was saying, that the calculator is very, very low resolution. So it's actually, I mean, this is totally not the graph of the function, not the correct looking graph, but it's not like the calculator is lying. It's just that the calculator doesn't have enough resolution to draw the rest of the graph, and the pixels are too big on the screen. So again, you've got to be careful. We jump back to the picture. You've got to know that log functions, so you got to know what they look like. Like this right here, that's what a log function in general looks like. You need to have that shape very clear in your mind, so that when you see something like this on a calculator screen, you're like, wait, that's not even what a log function looks like. That's wrong. So you just got to be really careful if you're using your calculator to check these. Well, that was just a quick introduction, and good luck with all of your exponential and logarithmic graphing.